So now we'll look at some specific subspaces of Rn. The null space first. Null space of a matrix A. So the null is referring to this zero vector here. So pause and copy if you haven't done so already. So the null space, this is the set of vectors that are, I don't know what you want to say, killed by A. So if A times X is a zero vector, then X is in the null space. If not, then not. So let's do an example to illustrate that. So to check if U is in the null space, all I do is calculate A times U. And what do you get? You get 5, minus 9 plus 4. Then minus 25 plus 27 minus 2. So you do indeed get the zero vector. Therefore, my answer here is yes. AV. Let's see if this one is 0. Well, right away, I can see that it's not, right? Not the zero vector. I didn't even bother calculating the second component because I could see that the first component was not going to be 0. Mathematicians are lazy that way. Okay, here if you have A times 0 vector, okay, that's obviously the 0 vector, so the 0 vector is always in the null space. Okay, so null space always contains 0 vector, which leads us to think about the null space in terms of subspaces. Is it a subspace of Rn? Yes, it is. Okay, we can see here that it contains a 0 vector. And for the remainder of the proof, I leave this to you as an exercise. These subspace proofs do not go away, so I recommend you pause and give this a thorough attempt. If you are not certain of your answer, then send it my way and I will gladly have a look. Okay, very important at this stage to get these types of things out of the way before we move on. Okay, now we'll talk about finding a null space given a matrix. So if I give you a matrix 1 minus 6 4 0 0 0 2 0, I'll just say find null A. Okay, describe it to the best of your abilities. For now, it's a 0 there. For now, we will say, well, what is null A? Well, it's, if you think about it, it's something we've seen before. It's a solution set to this equation, this homogeneous equation. So you write something like X is in null A if and only if AX is 0, right? So we end up solving this system. with another bunch of zeros on the end. So we solve this as usual. What do we get? 1 minus 6, 0, 0, 0, 0, 0. That must be a 1. I'm skipping some steps here, but so what it is now, I have REF. Very important. You need REF before you complete your solution here. So where are we? Convert back to equations. X1 minus 6x2 is 0. X3, 0. X4 is free. So this X, so a typical X that is in our null space, has 4 entries, X1 through X4. I make my replacements according to my general solution here. Oh, I forgot something. X2 is also free. Okay, don't forget this. X2 is free, X3 is 0, X4 is free. Pulling this apart, we get X2 times 6, 1, 0, 0. X4 times this vector. Okay, so what have we demonstrated here? Okay, we have demonstrated that if I have a vector x in the null space, it must be of this form here. So what does that tell me? Null A can be written down. Let's say that again. If I have an x in null space, it is a linear combination of this vector and this vector. It tells me my null space is the span of 6, 1, 0, 0, comma, 0, 0, 0, 1. And that's a pretty good description right there for our null space. This is called a spanning set. A spanning set for null A. Okay, because it's a set that spans the subspace in question. So here's my answer to the question I posed. Let's say a bit more about this, though. So this spanning set is independent, if you think about it. I want to say that, in fact, if I follow this method, then the set I get here will always be independent. So this set that came out, okay, without the span, will always be independent. if I follow the method, meaning if you have to make sure you reduce to reduced echelon form. Okay, that fact takes a bit of thinking about, but I'll just leave that alone for now.